Portsmouth Naval Shipyard in New Hampshire marked a somber anniversary today. It was 50 years ago today that the USS Thresher, a nuclear-powered attack submarine, sank and broke apart during a test dive off Cape Cod.
The catastrophe that swallowed USS Thresher always carried an unsettling weight, even in the earliest hours after the submarine vanished. Families waited for answers that never seemed complete, and experts studied fragments of data that pointed in troubling directions without ever forming a perfectly clear picture. Over time, however, as more technical records were declassified, as naval architecture advanced, and as investigators pieced together the operational context of the final dive, a far more detailed and sobering understanding emerged. It did not rely on rumors or dramatic revelations. Instead, it came from meticulously analyzing how a sequence of technical vulnerabilities and design assumptions converged into a disaster that no one aboard could escape. The closer that analysis came to a full explanation, the more it revealed a grim truth. The loss of Thresher was rooted in systemic issues rather than a single malfunction, and the implications reached far deeper than anyone initially wanted to admit. Before we start, smash the like and subscribe buttons for more updates. USS Thresher was a vessel born from the Cold War drive for technological superiority. It embodied advances in sonar, propulsion, quieting, and deep diving capability that promised a new generation of American submarines would be faster, stealthier, and more lethal than their predecessors. The enthusiasm for innovation was immense, and Thresher represented a leap forward so significant that the Navy viewed it as a prototype for future designs. Yet this atmosphere of urgency and aspiration also created intense pressure. Schedules were aggressive, new fabrication techniques were embraced quickly, and confidence in engineering methods often outpaced the rigorous testing those methods required. When the submarine slipped beneath the surface for what should have been a controlled set of deep dive trials, the crew carried not only the pride of pioneering sailors, but also the burden of participating in a test program that operated closer to the edge of uncertainty than anyone fully recognized. The event sequence leading up to the sinking began innocuously enough. Thresher descended in stages, accompanied at a safe distance by the rescue ship USS Skylark, which maintained communication by underwater telephone. The reports exchanged early in the dive suggested no major departures from plan. But around test depth, Thresher transmitted that it was experiencing minor difficulties, a phrase that masked a deeply perilous situation. Behind those words was a cascade of mechanical and environmental interactions that would have been invisible to anyone not on board. The submarine was likely reacting to a sudden flooding event, which in a deep-diving submarine transforms from a manageable emergency into a lethal one within seconds. Water rushing into a compartment is not simply liquid intrusion, it brings crushing pressure, a downward force that alters buoyancy, and a demand for immediate isolation that cannot tolerate hesitation. One of the core revelations from later analysis is that the probable source of that flooding came from vulnerabilities in the silver braze joints used in the submarine's pipes. These joints, while approved at the time, were not uniformly reliable under extreme pressure cycles. Tests conducted after Thresher's loss suggested that a non-trivial percentage of such joints across the submarine fleet could fail under simulated deep dive conditions. Thresher may have been at the very limit of what those joints could withstand. Even a hairline crack at depth could allow super-pressurized seawater to jet into the submarine with such force that it would instantly overwhelm equipment and cause critical systems to shut down or short out. In the tight confines of a submarine hull, the difference between a small leak and uncontrollable flooding is measured in moments, and once water begins pouring in, the submarine's descent can accelerate dramatically. As Thresher fought this emergency, the crew attempted standard recovery procedures. The submarine was designed to blow its ballast tanks, forcing air into them to create positive buoyancy and drive the vessel upward. However, the deeper a submarine goes, the colder the surrounding seawater becomes, and the moisture in the high-pressure air flasks used for blowing ballast can freeze the lines. If ice formed during Thresher's attempt to surface, the emergency blow system could have become partially or fully obstructed. Tests performed after the incident revealed that the air systems of the era were indeed susceptible to such freezing, particularly during rapid, deep-water ascents. This vulnerability meant that even if the crew acted perfectly and immediately, the physics of compressed air expanding into frigid pipes might have sealed their fate. Communication logs from the escort vessel reinforce another critical detail. Thresher did not suddenly disappear, but instead seemed trapped in a slow fight against increasing depth. Skylark received garbled messages suggesting the submarine was attempting to blow, but was not able to surface. In the final seconds, the submarine likely exceeded its crush depth. At such depths, structural integrity becomes a razor-thin threshold. Once the pressure surpassed what the hull could withstand, the catastrophic implosion would have occurred almost instantaneously. The energy release of an imploding submarine is immense, not an explosion, but a collapse so violent that it pulverizes internal structures in fractions of a second. There would have been no time for anyone aboard to react. What makes the more complete analysis worse than many had initially believed is not simply the technical explanation of a flooding event and failed ballast blows. It lies in the combination of systemic oversights, misaligned priorities, and assumptions about safety margins that proved tragically flawed. Thresher's design embodied groundbreaking innovation, but it also depended on fabrication techniques whose reliability had not been fully validated. Inspection processes were not yet rigorous enough to detect the hidden weaknesses in critical joints. Safety testing did not stress systems under the full range of conditions they would face during deep dive trials. The submarine community at the time operated under the belief that redundancy and engineering excellence provided a wide buffer, but Thresher's loss demonstrated that this buffer was far narrower than assumed. This realization is unsettling because it reframes the disaster not as a freak accident, but as the product of structural issues in how complex military systems were developed and certified. The drive for technological advancement had outpaced the maturity of quality assurance frameworks. Engineers working with limited data and accelerated deadlines could not fully anticipate the interactions between multiple emerging technologies under extreme conditions. Processes that seemed adequate on paper were not always sufficient in practice. The discovery that so many silver braze joints across the fleet might be vulnerable to failure meant that the issue was not isolated. It was systemic. The flawed logic that, if it passes inspection, it must function at depth, had permeated the design culture, and Thresher became the proof that this assumption could be fatal. Another dimension of the event's implications lies in its challenge to traditional notions of safety hierarchy. Submarine designers had long believed that emergency blow systems could reliably counter most forms of flooding unless the submarine was catastrophically damaged. The revelation that those same emergency systems could fail in an operationally realistic scenario was deeply alarming. It forced a new understanding that environmental conditions, such as temperature at depth, could compromise equipment precisely when sailors needed it most. What appeared to be a robust safeguard was, in fact, vulnerable under the exact conditions it was meant to overcome. Technical findings also pointed to issues with the submarine's electrical network. Flooding, even localized, could cause shorts that knocked out key systems. If the reactor scrambled automatically as seawater intrusion or electrical anomalies were detected, propulsion would have been lost at the worst possible moment. A submarine without propulsion is a submarine without control over its ascent or descent. As the ballast system struggled, the crew may have faced a simultaneous loss of forward motion, reducing options for managing buoyancy. These interacting failures, pipe rupture, flooding, loss of propulsion, potential ice blockage in airflow lines, created a multi-layered crisis that no single emergency response could resolve. The idea that the submarine succumbed to one fault is far less accurate than the conclusion that several small vulnerabilities aligned into a disaster that overwhelmed even a highly trained crew. The implications stretch further into the realm of organizational behavior. Complex systems often fail not because of one catastrophic flaw, but because numerous subtle weaknesses accumulate unnoticed. Thresher's story became an early and painful illustration of this principle long before it was widely recognized in engineering and safety culture. The gaps in inspection standards, the untested assumptions about airflow reliability, the incomplete understanding of deep water emergency dynamics, and the hurried pace of Cold War innovation all mingled into a scenario where a submarine that represented technological ambition also carried hidden fragility. The later, more complete picture revealed just how invisible those vulnerabilities were to the people who had trusted the systems with their lives. Understanding these deeper layers also underscores the immense bravery of the crew. They were not simply conducting routine tests, they were serving as the human interface between cutting-edge technology and the unforgiving environment of the deep ocean. Their actions in the final minutes were almost certainly disciplined, rapid, and technically correct given the information available to them. The tragedy is that no amount of individual competence could overcome systemic flaws embedded in the vessel's design and certification. This realization amplified the emotional weight of the incident. The loss was not due to inexperience or error, but to underlying issues that only became fully understood long after the submarine disappeared. One of the most profound implications came from the recognition that catastrophic failures often reveal the gaps in safety culture more clearly than any inspection report ever could. Thresher exposed a misalignment between the pace of technological advancement and the rigor of quality control. Innovations that seemed revolutionary carried vulnerabilities that had not yet been meaningfully tested. The pressure to field new capabilities quickly meant that deep system interactions were not always evaluated under worst-case conditions. These are not unusual issues in periods of intense technological competition, but in submarine design, where the operational environment is inherently hostile, they become especially dangerous. The deeper analysis also expanded the understanding of how submarine systems interact under cascading failure conditions. Conventional thinking had long held that submarines either experienced isolated malfunctions that could be addressed individually or suffered catastrophic damage from external forces. Thresher demonstrated that internal system interactions could create a catastrophic chain reaction without any external threat. This realization had profound implications for how future designers approached redundancy, fail-safe mechanisms, isolation capabilities, and emergency recovery systems. The idea that a submarine might experience multiple simultaneous failures, each compounding the other, changed the entire engineering approach to underwater vessels. The incident also influenced broader thinking about how complex machines are evaluated. Traditional inspection methods focused on checking individual components for defects. The emerging understanding from Thresher's loss showed that the interactions between components, particularly under extreme conditions, were as important as the integrity of each piece. This insight paved the way for more holistic evaluation methods that treat a submarine not as a collection of isolated systems, but as an integrated organism whose behavior must be understood under dynamic stress conditions. Such an approach would later become standard in high-risk engineering fields, but at the time, it represented a dramatic shift in perspective. Another implication lies in operational doctrine. Submarines are inherently at risk during deep dive trials because they are pushed to the edge of their design envelopes, and Thresher demonstrated that safety measures were not adequate for such tests. The deeper understanding of the event led to an appreciation that safety protocols need to be more than procedural steps. They must be built into the architecture of the vessel and the culture of the organization. A submarine undergoing deep dive testing must not only have reliable systems, but also layers of fail-safes that can operate independently of vulnerable components. Thresher's fate revealed that redundancy can fail if all redundant pathways share the same underlying vulnerability. Perhaps the most sobering implication is the realization that even advanced technologies can harbor fundamental weaknesses invisible until conditions push them beyond theoretical limits. Thresher was celebrated for its cutting-edge design, yet the very innovations that defined it contributed to its vulnerability. The push toward greater depths strained fabrication techniques not fully optimized for such conditions. The drive for quieter operation introduced new materials and joint designs whose long-term behavior under pressure cycles had not been completely characterized. As a result, the submarine's greatest strengths also contributed to the chain of events that led to its loss. The evolving understanding of the incident also influenced how naval organizations viewed transparency and internal learning. In the immediate aftermath, information was scarce, not because of deliberate secrecy, but because investigators lacked a clear picture. As more thorough analysis accumulated, it became apparent that openness about failure was essential for improvement. This realization eventually shaped how technical communities share information and how they approach fault analysis. Thresher's loss became a case study in the importance of acknowledging uncertainty, questioning assumptions, and challenging established practices when exploring the root causes of catastrophic failure. The event's implications extended beyond engineering and organizational analysis. They also shifted the cultural understanding of risk in submarine operations. Deep water missions inherently confront extreme forces, and the margin between safety and disaster can be razor thin. Thresher revealed just how narrow that margin can be. It demonstrated that confidence in engineering must always be tempered by vigilance, that redundancy must be tested under realistic conditions, and that the ocean does not forgive complacency. The closer the understanding came to a full explanation, the more it showed that the submarine had been operating on the edge of safety without fully appreciating that edge. The unfolding analysis also reframed how the naval community viewed the relationship between technological ambition and operational safety. The impulse to innovate is powerful, especially during times of geopolitical competition. But Thresher illustrated that innovation must be matched by equal investment in testing, validation, and quality control. The sinking became a sobering reminder that cutting-edge systems demand heightened scrutiny, not reduced caution. The early assumptions that newer meant safer proved dangerously incomplete. Technical marvels can harbor flaws that only emerge under stress, and those flaws can have devastating consequences when lives depend on flawless performance. Understanding the Thresher event more fully also sheds light on how submarine crews mentally prepare for the inherent dangers of undersea operations. Submariners accept risks as part of their profession, but the Thresher analysis revealed how much those risks depended not only on training and skill, but on the reliability of equipment they cannot see or directly verify. This raised important questions about trust, responsibility, and the relationship between sailors and the systems they operate. The submarine community has long emphasized that the vessel is only as strong as its weakest component. The deeper understanding of Thresher's loss reinforced just how true that mantra is. In the broader context of naval history, the Thresher tragedy marked a turning point in the relationship between engineering assumptions and operational reality. It highlighted the dangers of relying too heavily on theoretical performance projections without validating those projections under real-world conditions. It revealed how hidden weaknesses in fabrication, inspection, and system interactions can lurk beneath the surface of even the most advanced vessels. And it demonstrated that catastrophic failures often arise not from a single dramatic flaw, but from the accumulation of multiple subtle vulnerabilities. Despite the enormity of the tragedy, the evolving understanding of the incident also contributed to a profound shift in engineering philosophy. The analysis showed that safety cannot be assumed, it must be demonstrated. It cannot be added at the end of a design process, it must be built into every stage. This shift in thinking reshaped how complex systems are conceived, tested, and maintained. It also laid the groundwork for more rigorous engineering practices that extended far beyond submarine design. As the picture of Thresher's final moments became clearer, the implications reached beyond the immediate event. The lessons drawn from the analysis influenced discussions about risk, uncertainty, and the responsibilities of those who design, build, and operate complex machines. The realization that seemingly small vulnerabilities could combine into catastrophic failure challenged long-held beliefs and ushered in a new era of scrutiny and rigor. The submarine's loss became not just a tragedy, but a catalyst for deeper understanding of the limits of technology and the necessity of constant vigilance. The refined understanding also highlighted the profound human dimension of the event. The crew faced their final moments not in chaos or confusion, but in a battle against forces that exceeded the capacity of their equipment. Their struggle illuminated the stark reality that even the most highly trained sailors can be placed in situations where success is impossible because the systems supporting them are flawed at a structural level. This aspect of the analysis underscored the importance of recognizing and correcting vulnerabilities before they manifest, because those who serve rely entirely on the engineering decisions made long before they ever set foot aboard a vessel. The implications of the Thresher event therefore resonate far beyond the submarine community. They speak to universal truths about engineering risk, systemic oversight, and the need for rigorous evaluation of critical systems. They remind us that complex machines demand not just innovation, but humility, an acknowledgement that even advanced technology must be scrutinized with an eye toward the unexpected. As the layers of the incident were peeled back over the years, the emerging picture did not reveal a single hidden culprit, but rather a network of contributing factors that, together, formed a scenario far more troubling than early assumptions suggested. It is this cumulative understanding that makes the fuller picture of the USS Thresher tragedy feel worse than the early narrative. It is not simply that a system failed, but that multiple systems failed at once. Not simply that a flaw existed, but that flaws existed across multiple domains: fabrication, testing, system design, and operational assumptions. Not simply that a submarine was lost, but that the loss revealed vulnerabilities that extended across an entire generation of vessels. The event became a stark demonstration of how deeply the quest for advancement must be paired with rigorous safety oversight. The evolving understanding of what happened to USS Thresher does not rely on sensational revelations or rumor. It arises from patient analysis of technical data, engineering reports, and historical context. It paints a sobering picture of a vessel pushed to the limits of its design, carrying hidden flaws that only became visible under the crushing pressures of the deep. It reveals that the tragedy was not the product of one catastrophic failure, but the culmination of systemic vulnerabilities whose implications extend far beyond the confines of a single submarine. The picture that emerges is one of innovation shadowed by risk, progress pursued without fully grasping its hidden costs, and a vessel that represented both the aspirations and the vulnerabilities of its era. The deeper the analysis goes, the more it underscores how thin the line can be between groundbreaking achievement and catastrophic failure. And in the story of USS Thresher, that line became visible only after it had been crossed, leaving behind a legacy of lessons etched into the history of submarine design and the understanding of how complex systems behave under extreme conditions. The deeper layers of the USS Thresher analysis reveal another unsettling dimension: the way uncertainty itself becomes a force in catastrophic events. Thresher's final dive illustrated how unknowns, those factors engineers did not realize they needed to consider, can become as dangerous as any mechanical failure. Understanding this aspect requires looking at the submarine not from the perspective of what failed, but from the perspective of what was not yet understood about the nature of deep ocean operations. This involves recognizing the ocean as an environment that magnifies small design assumptions into enormous consequences. Pressure increases at a rate that does not permit gradual adaptation, and any system operating at those depths must respond instantly and flawlessly. The refined analysis makes clear that several of Thresher's systems, though advanced for their time, were not designed with the full spectrum of possible deep-water interactions in mind. One of the complexities often overlooked is the behavior of materials themselves at extreme depths. Metals, seals, and joints do not simply act as they do at shallow depths. Under immense pressure, they deform, contract, and flex in ways that alter how connected systems interact. Thresher's designers accounted for known behaviors, but the later understanding makes clear that some stress patterns were not fully appreciated. For instance, distortions in piping systems under compression could subtly shift angles or strain braze joints in unexpected ways. Even if a joint passed inspection at atmospheric pressure, or even after controlled test pressurization, the real ocean introduced dynamic forces that were not perfectly reproducible in testing facilities. The analysis revealed that these unpredictable microbehaviors of materials created opportunities for failure that went unnoticed during construction and evaluation. Another dimension that emerges when examining the event more deeply is the significance of time. Submarines operate in a continuous negotiation with the ocean, their systems constantly adjusting to maintain equilibrium. For a vessel like Thresher, which was undergoing deep dive trials, the rate at which the submarine descended mattered as much as the depth itself. Small increases in descent rate can dramatically intensify system strain. The refined understanding of the timeline suggests that the submarine's descent after the initial emergency may have accelerated gradually rather than suddenly, placing sustained stress on multiple systems at once. This prolonged strain could have exposed weaknesses that would not have been problematic during a rapid, controlled descent or moderate depth operation. The analysis shows how time, pressure, and system interactions created a compounding environment of vulnerability. A similar consideration arises in understanding how human decision-making interfaces with complex systems. Submariners are trained to respond to specific cues, but when multiple cues appear simultaneously, or when cues contradict expected patterns, the cognitive load becomes immense. The deeper study of Thresher's situation underscores that the crew faced not a single emergency with a clear path to resolution, but a convergence of alarms, indications, and system behaviors that would have been difficult to interpret in a rapidly changing situation. Submarines are designed with the assumption that crews can isolate failures, but Thresher's crisis challenged that assumption by presenting overlapping symptoms whose root causes were not immediately distinguishable. The refined picture suggests that even if the crew recognized flooding as the primary issue, the associated electrical effects, propulsion changes, and buoyancy complications would have created a complex scenario with rapidly diminishing options. A fuller appreciation of the event also brings attention to the nature of testing protocols for cutting-edge vessels. Deep dive trials are essential, but they also expose submarines to the highest risks they will ever face outside combat. Later evaluations made clear that early dive tests for new submarine classes involved assumptions that had not been sufficiently validated. For example, it was believed that structural tolerances incorporated enough margin to negate minor fabrication variations, but closer analysis showed that this assumption was overly optimistic. Similarly, the reliance on theoretical models to predict how systems behaved at depth meant that real-world testing was effectively the first opportunity to observe true system interactions. Thresher's loss demonstrated that certain kinds of system behavior cannot be reliably predicted through simulation alone. Only actual deep-water conditions reveal how complex assemblies behave when subjected to the combined forces of pressure, temperature, and motion. Another aspect that gained clarity with time is the role of acoustic environment. A submarine under high strain can generate noises from metal, flexing, shifting components, and pressure equalization. These noises can mask other critical sounds, making it harder for the crew to detect leaks or abnormal vibrations. The growing understanding of Thresher's situation suggests that acoustic masking may have obscured early signs of escalating issues. If small leaks or structural creaking occurred before the major emergency, they might have been lost in the ambient sound of a submarine being pushed toward its operational limits. This raises important questions about how much early warning capability crews truly had, and whether certain cues were indistinguishable from background noise until the situation had already deteriorated. Examining the event through a broader engineering lens also highlights the challenges of integrating multiple advanced technologies into a single platform. Thresher was a pioneering vessel, incorporating innovations in propulsion, sonar, quieting techniques, and structural design. Individually, these technologies represented significant progress, but collectively they created a level of system complexity that pushed contemporary engineering oversight to its limits. Systems designed by different teams, built in separate facilities, and tested under varying procedures were combined into a single platform expected to perform flawlessly in the harshest environment on Earth. The deeper analysis reveals that when multiple state-of-the-art technologies are integrated in this way, unforeseen interactions can arise. The submarine's propulsion behavior, electrical network, and piping systems were interconnected in ways that were not fully appreciated at the time of construction. An additional dimension becomes clear when considering the limitations of inspection technology available during the period. Many of the submarine's joints, welds, and structural interfaces were examined using methods that could detect surface defects or significant internal flaws, but were less capable of identifying microcracks or imperfections that could expand under pressure cycles. Later advancements in non-destructive testing techniques showed that some weaknesses hidden deep within braze joints would have been undetectable with the tools available when Thresher was built. This realization adds another layer of complexity to the event. Certain vulnerabilities existed not because they were overlooked, but because they could not yet be seen. The submarine operated at a technological frontier where inspection, fabrication, and operational demands advanced at different speeds. A more nuanced understanding of the tragedy also brings attention to the nature of redundancy within critical systems. Redundancy is often assumed to be a guarantee of safety, but true redundancy requires that backup systems operate independently and are not susceptible to the same failure modes. In Thresher's case, later analysis suggested that several redundant pathways shared underlying vulnerabilities. For example, the ballast systems depended on air supplies that could be compromised by freezing. Electrical redundancy could be undermined by flooding-induced short circuits. Even propulsion redundancy had limits, since certain electrical anomalies could cause automatic reactor behavior that stripped the vessel of forward motion when it was most needed. This interconnected vulnerability shows how redundancy can provide a false sense of security if all paths rely on components that fail under similar conditions. Further analysis also highlights the role of pressure differentials in accelerating system failure. A submariner's instinct might be to classify flooding as a localized emergency, but at extreme depth, the pressure differential between the ocean and the submarine's interior creates force levels that escalate rapidly. A breach only a few centimeters across can admit water with such power that it pulverizes equipment, dislodges fittings, and overwhelms pumps instantaneously. The refined picture of Thresher's final moments suggests that even a small leak, once initiated, could have expanded due to pressure-induced deformation, turning a manageable situation into a catastrophic one within seconds. This dynamic was not fully understood at the time of the submarine's construction, and the evolving understanding of these pressure effects has since shaped how deep-diving vessels are designed. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what really happened to USS Thresher in this disaster? We want to hear from you. Thank you for watching and see you next time.